Well, so today also we means in this particular class also we continue with our phase equilibrium discussions, and we had already discussed the vapor liquid equilibrium and the solubility curves. The next operation which is there is the liquid solid adsorption and the gas solid adsorption, and definitely after that the liquid liquid equilibrium conditions. Now, just if you recollect that in the first class on phase equilibrium, what we had discussed, that the units in which we express the concentration. When we were discussing that, I had mentioned that usually while in the gas phase, we do it in terms of partial pressure. In the same way, for the liquid phase, we express it either in terms of mole fraction. There is one thing which I had forgotten to mention in the class was that apart from mole fraction, there are also cases where we adopt the mole ratio. What is the mole ratio? The mole ratio is normally we express it in terms of capital letters. So, xi this is equals to the moles of the component I say in terms of the solute free solvent or this in terms of the solute free mixture. Okay. In the same way, if we are dealing with the gas phase and the liquid phase or the vapor and liquid equilibrium, we instead of xy data, we can also represent the equilibrium in terms of capital X and capital Y data, where these are known as the mole ratio. The advantage of using capital XY and XI and capital YI is that this very often leads to your linear plots, and that is definitely quite a advantage for us. Anyhow, now coming back to adsorption, very conventionally normally what we find is that we just as I have told you that when it is a gas solid case, under that condition we express the y axis in terms of q, where q it is equal to the adsorbed mass or the mass which has been absorbed divided by the mass of solute free adsorbent. Now, before I start the equilibrium, I would like to mention that when we are having the process of adsorption, then the component which is adsorbed, that component is known as adsorbate. That means component which is adsorbed, and the solid which adsorbs this component, that is known as adsorbent, right. This is the component which adsorbs, and what does it adsorb? It adsorbs the adsorbate. So, therefore, in this particular case, it is the adsorbed mass of the adsorbate divided by the mass of the solute free adsorbent, right. And the x axis, this has been shown for a liquid solid adsorption. So, therefore, it is shown in terms of Q versus C, where this particular concentration, this can be that it can be either PP, if it was a gas, then it would have been the partial pressure of the adsorbate in the gaseous mixture, which is denoted by Pi, and for the liquid solid case it is denoted by Ci, which is the adsorbate concentration in the liquid solution from where the component has to be adsorbed, and this Ci, this is frequently it is expressed in terms of, it can be expressed in moles per meter cube, or maybe in terms of kg per meter cube, or maybe in terms of parts per million also it can be expressed, right. So, therefore, for adsorption if you see you will find that generally whatever be the units, this is the general type of graph that we find in this particular case, right. Now, let us discuss the effect of the different measurable parameters on the adsorption curve. Say for example, temperature. What do you expect is going to happen when, suppose with increase of temperature, how do you think that this particular curve it is going to change? Again I would like to remind you, adsorption is an exothermic process. It is accompanied by release of heat, just like I had told you about absorption. So, therefore, if it is accompanied by release of heat, from Van 't Hoff's law what do we know? As we go for higher temperature, adsorption it decreases, right, or rather as we go to higher temperature, the adsorbate loading at the constant solute partial pressure for gas adsorption and also the at a constant concentration of the solute in a liquid solution. As we go for higher temperature, the adsorbate loading or Q it decreases, right. So, with increase in temperature we find that Q decreases at a constant P, we get something of this sort, right. What about the partial pressure of the solute? For a liquid solid adsorption this should not matter, but for a gas solid adsorption quite naturally when we go for a higher pressure it increases the loading at a constant temperature. So, if the temperature is kept constant, as we go for higher temperature, this higher pressure, the loading increases. So, first we discuss the effect of temperature. So, we find that with temperature adsorbate loading decreases. Then solute partial pressure, as we increase it, it increases adsorbate loading. This solute partial pressure it can be increased by increasing the amount of solute in the gas phase and or by any particular way if we can increase the solute partial pressure it increases. There is one other thing also which is important in adsorption which did not occur in vapor liquid equilibrium or in your solubility curves is the specific surface area, because we need to remember that adsorption it is a surface phenomena, right. So, therefore, if we increase the specific surface area or if we increase the porosity of the medium, naturally the total area available for adsorption increases, and so naturally whenever we go for higher porosity it ensures higher specific surface area. So, therefore, larger adsorption capacity per unit weight of the adsorbent, or in other words this also increases Q. The next thing is which again influences this particular adsorption curve, it is the nature of the solute. How does nature of the solute it influence the adsorption this particular adsorption curve, if you can tell me? We find out that for vapors and gases with high molecular weight, I would like to write it here, for vapor or gases at high molecular weight and low critical temperature, or in other words low Tc, these are more readily adsorbed, they are better adsorbed. Comparatively, we find that permanent gases they are less readily adsorbed. The same way polar molecules are better adsorbed. So, therefore, vapor or gases at high molecular weight and low Tc they are better as adsorbed, permanent gases they are less readily adsorbed, and also polar components they are also much better adsorbed. So, they also give a higher adsorbent loading, and this explains why water is much more readily adsorbed as compared to say hydrocarbons, etc. Right. Now, there is one other thing that I would like to mention, that is that I have already mentioned that more or less the Q versus your concentration curve, where it is usually concentration in the liquid phase and the partial pressure in the gas phase. So, for this particular curve, it is more or less it has the same characteristics. The only thing is that for the liquid solid case, it is not influenced by the solute partial pressure. Otherwise, more or less it is same, but there is something very interesting when we talk about the liquid solid adsorption. If we start with the fresh adsorbent and we start it, what happens even if we start with some particular very inert solvent also, under that condition also initially some amount of solvent that gets occluded into the pores of the adsorbent. Now, moment some amount of solvent goes and gets adsorbed, quite naturally the CI it increases. This CI, the point is, in this particular case we find it actually appears, which is evident from this particular portion of the curve, it actually appears that the your Q it actually becomes negative under such particular condition. And therefore, under these conditions it is important that we consider the apparent weight of the solute adsorbed per weight of the adsorbent. Now, the curve which I have drawn in this particular case, the curve A, that denotes adsorption from a dilute solution where the negligible solvent is negligibly adsorbed, or in other words negligible adsorption of solution, a solvent, right. Now, this is the curve which normally happens. So, for this particular curve we find that this is the curve that we would expect, but when we find that the solvent is appreciably adsorbed, under that case we actually have a curve something of this sort, where this particular part D to A, under this condition the solvent is actually more strongly adsorbed by the as compared to the solute. So, therefore, we get compared to solute. So, therefore, we get a curve something of this sort over certain range of conditions. So, therefore, this particular thing has to be kept in mind when we are dealing with liquid solid adsorption cases. Well, for the adsorption, if you find that you see that just like we have there are equations which are available to generate vapor liquid gas solubility data, in the same way we find that there are also equations which are available in order to express Q in terms of P and T. Now, remember one thing, that normally these things they are expressed, the most common way of expressing adsorption are in terms of isotherms. So, therefore, we find that for most of the cases we express the adsorption in terms of isotherms, or in other words usually we express them in terms of Q as a function of P at constant T. Expressing Q as a function of T or expressing Q as a at constant P, or maybe expressing P as a function of T at constant Q, which is known as isostir. So, therefore, more than these two, this is much more common, and therefore, we find that there are a large number of equations which are available for expressing adsorption isotherm. All these equations which are available, they stem out from a Henry's law sort of an equation which tells Q is equals to say some particular constant, say B or A or whatever, into C star. So, this is the basic equation. This equation is the simplest adsorption isotherm. From this particular equation, this is modified to account for the actual situation, and there are a good number of equations. The assumptions for the different equations are all written, and from whatever is written you can very well understand that although the Fredlich equation, it is much more used, it is the most commonly used equation, but then also it is thermodynamically inconsistent. On the other hand, you will find that Langmuir equation, it is, although it is not so much used, but this is much, it is theoretically justified. Why do we call that this is thermodynamically inconsistent? Because it does not have a finite Henry's law constant. So, therefore, this is thermodynamically inconsistent, but nevertheless this equation is the most commonly used equation. In this particular equation, if you observe, you will find that when Kc is equals to 1, under that condition we find that the isotherm is linear, and when Kc is greater than 1, under that condition, what do you find that for this particular condition the isotherm is concave upward, and this gives this indicates good adsorption capacity. Normally we find that 2 less than Kc less than 10, this predicts very good adsorption capability, and 1 less than Kc less than 2, that means a value of Kc between 1 and 2, that represents moderately difficult adsorption capacity, and if we have Kc less than 1, then definitely it shows very poor adsorption capacity. So, therefore, if we would like to select an adsorbent, we would like to ensure that the Kc value it's greater than 2. In that particular case, it represents that the adsorption is going to be effective in this particular case, right. And we definitely not select any particular adsorbent which yields a Kc which is less than 1. Well, so with these things said, we have discussed adsorption. The next thing which is there, it is the liquid extraction. In liquid extraction, what do we have? For liquid extraction cases, we introduce one particular liquid into another particular liquid mixture. Say we have a mixture of say A plus B. What do we add here? In this particular liquid mixture, say we add some particular solvent S. What do we expect? Maybe we would like to remove B from A. So, therefore, from here what do we expect to get? We would expect to get S plus B, which is known as the extract phase which has been extracted, and there also will be having some amount of B which is remaining in A, and this is known as the raffinate. But along with this, there is something more that we should remember when we are dealing with liquid extraction cases. No matter whatever solvent you use, even if the solvent and the basic solvent in the feed, even if they are chemically extremely difficult, there will always be some amount of miscibility between the two solvents. So, therefore, we will find that no matter whatever solvent you select, we will find that in the extract phase there will be some amount of A, in the raffinate phase there will be some amount of S. So, therefore, in this particular case what do we find? We find that the composition. So long what we were dealing with such particular situations where we found that more or less only one component was diffusing, and we could assume that suppose it is air, ammonia and water, the air does not dissolve in water. Even for vapor liquid equilibrium also we had assumed that for the two phases there were some components which were diffusing here, some components which were diffusing in the other direction. So, therefore, for a binary mixture, on a either the Tx can vary and we can find out Py, or maybe the Ty varies, we can find out Px, etc., etc. But in this particular case we find that both the phases have got all the three components which are available in this particular case. So, therefore, suppose we try to find out the fugacity of say A, right. So, the fugacity A in the raffinate phase should be equal to the fugacity A in the extract phase, or in other words gamma A x A should be equal to gamma A x A in the raffinate phase should be equal to gamma A x A in the extract phase. Same way we can say that gamma B x B in the raffinate phase should be equal to gamma B x B in the extract phase. Just likewise we can say, and remember one thing, since we are dealing with two liquid solutions, there is every chance that both of them are going to be non-ideal. So, therefore, gammas are extremely important in this particular case, and therefore, the process of finding out gammas are the same, but most of the cases we have to include the gammas in the phase equilibrium equations written down for liquid extraction cases. So, therefore, these are the equilibrium relationships coupled up with the fact that sigma x c should be equal to 1, sigma x a should be equal to 1, and sigma x b this also should be equal to 1. So, therefore, in this particular case the K I, the K factor or the equilibrium ratio that we have talked about, in this particular case it is generally denoted as the distribution coefficient, which is say x I in the extract phase by the x I in the raffinate phase, which is naturally gamma I, say I means in this particular case if B is the component, which gives you gamma B in the extract phase divided by gamma B in the raffinate phase. Once you can find out Kd, you can also of Kd for the component B, you can also find out alpha, and you can find out the expression of alpha. And just to show you that when we are performing the liquid extraction, we are actually operating in this particular zone. In this particular zone, as you can see, this is a typical liquid vapor extraction curve. We find that in this particular zone, when say one particular liquid is in a very small proportion, then they are miscible, in the two liquids are miscible. When say for example, the liquid 1 is in a very small proportion. So, therefore, when L1 is in a very small proportion, they are miscible in all proportions. When L2 is in a very small proportion, then also they are miscible in all proportions. Over some particular range, say for example, we have started with L2, pure liquid L2, and then we start adding 1 there. Gradually we find that there is one particular zone where we find that the Gibbs free energy of the solution is higher than the Gibbs free energy of the two components taken separately. If we can draw the Gibbs free energies, say the molar Gibbs free energy as a function of x, we find that for an immiscible system, we find that the Gibbs free energy over some range is actually higher. So, for this particular range we find that actually the two solutions, they would prefer to be separated than being in a solution. So, therefore, and remember one thing, that liquid equilibrium, that is influenced by temperature, but it is independent of pressure. So, we always would like to operate this at higher and higher pressure in order to ensure that this range, the existence of two liquids are can be extended over a larger range of composition, and we do not enter the vapor range. Suppose by any chance we reduce the pressure, then in that case we find that in that case the vapor liquid equilibrium sets in, but I will not be going into the details of all this. I would just like to mention that whenever we perform liquid extraction, we would like to operate in this particular zone. And as I have said that during liquid extraction, since all the components, even if it is a binary mixture, all the components are available in both the phases, normally the liquid that we add, that is known as a solvent. The original solution, it is a feed, and what has been extracted, it is the extract, which majorly comprises of S, very small amount of A, and something which is remaining, which majorly comprises of A, some amount of B which has not been extracted, some small amount of S. Therefore, since all of these are, all the compositions of all of these vary, therefore, in order to express liquid equilibrium data, normally what we have, we refer to ternary plots in order to find, in order to in order to depict the composition of all the three components on a 2D plot. Now, what is this ternary plot? In very briefly, if I can mention this, this particular ternary plot, if you find, this is represented in an equilateral triangle, where all the apices, they refer to the pure component. Okay, so this refers to 100% A, 100% B. A, B was the original solution to which we had given S. And the arm AB of the equilateral triangle, that refers to, or that corresponds to the composition of the solution AB, which was our original feed solution. As we move from A to B, we find that the proportion of B increases and the proportion of A decreases. When we add S, what happens? From this particular straight line joining A and B, we enter inside the triangle, and we enter into this particular portion, which is the three components system. Same way, if you refer to this particular arm BS, this gives you the composition of the solution of B and S, and same way this gives you the composition of the solution of A and S, and inside this all the three components are present. And you will find that moment you add S, the composition, it immediately shifts from the straight line inside the triangle, right? And when it shifts, here all the three phases are present. Now, since the solubility of S in A is very less, so therefore, we find that the curve, there is some particular equilibrium curve established between A and S. Now, the more they are insoluble, the closer will be these points to the two particular apices, and if they are less soluble, then they will be more removed from the apices. Now, we find that this corresponds to the solution of S in A, and this corresponds to the solution of A in S. We find that just like I had shown in the previous figure, in the same way we find that there is a range where this A and S are immiscible. Same thing I show here also, that there is a range where A and S are immiscible. So, when you and outside this range we have A, B and S miscible in all proportions, and therefore, we have one liquid solution here and we have two liquid solutions here. So, that automatically tells you that if you want to perform the liquid extraction, you need to perform within this particular dome. Suppose, say for example, you have this was the composition you have of the AB solution, you have added S, and now suppose the composition is at M. So, therefore, the overall composition of the ABS mixture is at M, which separates out into the raffinate phase composition corresponding to this and the extract phase with the composition, or rather with the proportion of S corresponding to this. So, therefore, this particular line which represents the raffinate and extract composition in equilibrium to the overall composition of the liquid mixture, this is known as a tie line. And you will observe that in this particular case you find that these tie lines, they are not parallel. Usually they slope in an upward direction and they gradually become smaller and smaller till finally it reduces to the point. This point, it is known as the plate point. Beyond this is the limiting condition for this immiscible zone. Remember one thing, this is rarely at the center, or rather these two curves, they rarely they meet symmetrically, and this is usually at one side, and this gives you the limit of immiscibility in this particular case. And since this is an equilateral triangle, so quite naturally we know that in an equilateral triangle, the sum of from this particular point, if we drop say perpendiculars to the three sides, then the sum of these perpendiculars is equal to the sum of the, or rather is equal to the altitude. So, therefore, if we take the altitude as the 100% of the entire composition, then we find that this length, this corresponds to the percentage of B, this particular length, this corresponds to the percentage of S, this particular length, this corresponds to the percentage of A in this particular case. And also from B, if you drop a, sorry, it became, if you drop a line here, then you find that this corresponds to the proportion of A and S in the solution. As we move along this line, the proportion of A and S remains constant. It is only B which is added up, and that changes the overall composition of the mixture. Now, rather than this, there is another much more convenient way of expressing the ternary system equilibrium, where we can express the compositions on a rectangular plot or in a right angle triangle, where we find that the composition of component B in the raffinate and the extract phase are denoted by the y axis. Composition of S in the raffinate and the extract phase are denoted in the x axis, and by difference from these we find out the composition of A. In this case also it's the same thing. We can show the two phase zone and the single phase zone, and the tie lines, everything can be shown, and corresponding to the two ends of the tie lines, just as we have drawn in Txy, Pxy and all plots. In this case also we can plot the proportion of B in the extract phase. Normally that is shown as Yb. If you use, you can also denote it as Xb in the extract phase, and the proportion of B in the raffinate phase. By convention, the raffinate phase composition is denoted by X and the extract phase composition is denoted by Y. So, therefore, in this sort of a XY plot, if we plot the end points of the tie line, we can get an equilibrium curve, And here you have to remember, since B is preferentially extracted by S, and so therefore, the curve lies above the y equals to x line. So, therefore, in short we have discussed the different equilibrium curves, the vapor liquid equilibrium, the gas solubility, the isotherms for adsorption and the ternary plot for liquid extraction. So, from this I wanted to give you an idea regarding the different equilibrium representations, how they are represented. There are mathematical equations available, there are also plots, there can be tables also available. The entire thing has emanated from thermodynamic equilibrium, which states that at equilibrium the chemical potential of each component in the different phases should be identical, or in other words, the fugacity of each component in the different phases should be identical, and based on that we can express the equilibrium data either in terms of your plots or in terms of K. The K values are usually used for ideal solutions, and they are very frequently used in hydrocarbon industries, because mostly those solutions, they are the hydrocarbons, they form the members of a homologous series. So, they form ideal solutions. Very frequently they are expressed in terms of alpha, which gives you the relative ease of separation. And just like we have equilibrium ratios or the K values for distillation, we have distribution coefficient for the liquid extraction cases, and just like Pxy, Txy, Xy, they are important for distillation. The your Pi versus Xi curves, they are important for absorption. Q versus Ci or Q versus Pi curves, they are important for liquid solid adsorption and gas solid adsorption respectively, and the ternary plots, they are important for liquid extraction. So, with this we complete the discussions on phase equilibrium, which governs the interphase mass transfer, and from the next class we start discussing individual processes. So, we plan to start with distillation and then proceed to the other operations or the other mass transfer operations, whose brief introduction has already been provided to you in the introductory lecture on mass transfer operations. Thank you very much.